Good morning, everyone. Can you hear me? Can someone confirm me if you can hear me? Hello? Good. All right, so let's wait for a couple of minutes and we'll start. Okay, let's start. Okay, so here are some announcements. So we are almost nearing the end of the class. Today is what? Today we are going to do lecture 12, curve fitting. And then there are 5 more lectures. This format allows me to finish the lectures a little bit fast because especially when I record, I can just compress it. Usually it doesn't. Usually I won't be able to finish a lecture in one class, but now probably it is possible. So that is going to give us some extra time towards the end, which I can do some revision, maybe doing some homework question. I'll do that, but yeah, I plan to finish one lecture at a time. Let's see how it goes today, because today's lecture is quite long. So there are announcements. First, homeworks. So I just uploaded homework 9, which covers today's lecture and Thursday's lecture. So there will be another 2 homeworks, 10 and 11, which will cover each 2 lectures each. So the last homework will be used after considering any extension December 1st. It can be extended if you want. Now the other thing is 2 homeworks with the lowest marks. I will reduce them. So I will just take all your homework marks and then find the lowest two, and then we'll exclude it before averaging. So now if you find some time problems, especially at this time where you have a lot of things, if you want to skip this homework, you can, but I wouldn't suggest that, because the whole point of homework is to learn. You're here to learn. So that, keep that in mind. I have this. The reason I have this, allowing lowest homework is mostly for students who, due to some reason, like sick or something, they couldn't do on homework. So that is really the reason for that. We have 2 more labs. I think lab 5 will be available this week, tomorrow, and then next week lab 6. After that, the remaining time, we will use the lab time to do a project. So I will give the details of the project very soon. And then quiz. So we already had 2 quiz. It is like MCQ. Maybe I will have another 1 or 2, maybe 3 quizzes. And if we have more than 3, I will also do the same, like homework. We are not definitely going to have more than 5 quizzes. So either another 2 quizzes, maybe 1. If I have like 4 quizzes in total, I will take the lowest one out of that. So that gives you something there. If you missed a quiz or something, you can use that, take advantage of that. The last day of class is December 9, Wednesday. I don't really need to I won't even be teaching anything on December 8, because I would have finished my lecture before that. But in those remaining lecture hours, I will be doing, just go back to, you can ask me. So we will have at least 3 lectures, at least, for this. So the week of December 7, and we will have the week of December 7, and then we will have the week of November 30th. So December 1, December 3rd, and December 7th is for reviewing. If we want me to do any questions from homework, I'll be happy to do that in class. I mean, if you don't ask, I will select a few questions and do it. So I hope, please make use of this time to ask me to review something. Or if you want me to review lectures, I will do that. Final exam. Final exam is, I'm sure you have it in your calendars. It is December 17th from 12 to 3 p.m. We did not have we had a midterm exam, but I made that into a programming exam. So I didn't really cover like theory. So that is why the final exam is going to be cumulative for lectures, but there's no programming. So it is only about understanding theory and doing these homework questions. In some of the homework questions, if you just go to my lecture notes and find out, for some of them I say, okay, this is final question 2019, things like that. These are questions I make for final exam and then put it at the back of lecture notes, and so obviously it grows with time. So practicing all the questions at the back of the lecture note will help you. So it is numerical method. That is what this course is. So you are free to use any program that you wrote, not something that is available or something. Any program that you wrote for the lab or something, you can use that during your exam. But end of the day, just if you take a look at the homework question, you have to decide which is the best way to do these questions that you have been doing in homework. Is it to write a program? Obviously, my program is timed. So it is going to be from 12 to 3, no extra time. I will give you 30 minutes extra time to scan and upload. So you will be writing the exam from 12 to 3, and then 3 to 3:30 you will be scanning and uploading it. You have been uploading homework, scanning and uploading homework homework and no one had any issue. So I don't really think, expect any technical problems there. Just you know how to do it. Just write it and scan it and upload it. So that's, I guess that's it about the final exam. So yeah, obviously it is open book. You can refer lecture notes, and then you can even use you can use your existing programs to get your answers. But you might have some experience from doing the homeworks. If you already have it, you might use it. But if you don't have it, probably. But I will make sure that the questions will be doable with a calculator. You won't need a program to do this. You won't need a computer program to do those questions. All right, those are all the announcements about the remaining lectures. We are almost nearing the end of this class. Okay, so I just uploaded these lecture notes. Please take a look. I'm going to just go through it. So this is lecture 12. Lecture 12, curve fitting. So what is curve fitting? Let me give some introduction to curve fitting. So let's say we have some points, some data points, x, I, y, I. So this is x-axis, y-axis, and we have some data points. x1, y1, that is x1, y1, x2, y2. One, two, three, four, five. There are 7 data points. Now, clearly there is a pattern of this data. Well, let's say we want to fit a line through these data points. Let's say a straight line. For this particular example, by looking at this, I can roughly say that line is going to be something like this. Because it goes through first of all, you cannot have a line that goes through all the points. If that line should go through all the points, that would be like, okay, that's a little bit complicated. So that's not possible. It cannot come back. So that's. But we will start with that. Now we will also study fitting those curvy lines later, but we will start with the straight line first. So if we had to do a straight line, which can be written as y is equal to a0 plus a1x. Now y is equal to mx plus c is what we studied. A0 plus a1x. So this is the c cutoff point. A1 is the gradient. Usually we use m. So obviously this is a0 because that is a cutoff point. So how to do this? How to find, so given some data points. So the problem, so this is the problem. Given data points, given some data points, x1, y1, x2, y2, xn, yn. Fit y is equal, well, rather than saying fit, I'm going to say find a0 and a1 such that y is equal to a0 plus a1x. Yeah, x and y will be used on this equation. So, okay, there were some questions. So Sydney is asking, no programming. Does that mean it's more math and work? Solution like the home? Yeah, homework is question is a good example. So the goal of the final exam is to have I am sure you have gained good experience programming all of these through the labs. But then this time my goal is to make sure you all review all this theory. A lot of theory I introduced, and then you prepared to express your understanding. So you have to be very. That is how I have been doing this past few years. So some of the homework questions, sometime I indicated, sometime I didn't, but I am still organizing them. But some of the homeworks questions you have are past final exam. So if you take any homework question, that is a potential candidate for final exam. Obviously, I won't have the same question from the homeworks. So that should answer your question. Now, do I have to write program C++ for homework question or on paper? I don't understand it. For example, let's say you have a homework question about polynomial fitting. So rather than if you look at it, the homework, I have 2 questions for you to solve. You have to fit a line for a given data. So you can write a program for that homework question, expecting that. So you're betting that, okay, maybe there will be a question about final, I'm going to use it. Feel free to do it. If I use code to answer a question, do I include the code too? No, you're not going to include the code. You're not going to check that. We don't just, we will only check. So you can use a code to get the answers, but then you have to go and express, you have to explain your understanding. Okay, this is this, and you have to explain it, because I'm here to, the goal of the final exam is to evaluate your understanding of the theory, because I have given you enough things to program through the labs, and in the homework you can program and test, and I have introduced enough the concept that everything that I have been teaching here can be programmed, and you're free to do that with the homework. That should give you enough experience. But in the final exam, I want to test your understanding of, okay, we did all this program, but do you understand the concepts? So so you can use a program to get the answers, but put them in a way that displays your understanding of the theory. I did many examples in the lectures. For example, we'll be doing some examples right now. So it's the same way. Okay, so I just introduced what is a linear curve fitting. And also I need to tell that there are many objectives. So given these data points, we can have many objectives to fit. For example, in the lecture note, I talk about 3 different objectives. One is to minimize the sum of all residual errors. So if I say residual errors, so let's say this is the data points. So that's the data points, and let's say this is the line we are fitting. Let's say this is the, oops. This is the line. So the error will be, how much. So there's a question. Last homework on bisection method has like 10 iteration. Do I have to? I will make sure that it won't come to that point. We will. I'm not sure if there's a homework that you had to do 10 iteration by hand. Let me see. Bisection. Can you tell me which question is this? Is it homework what? Homework 5? No, 4. Homework 4, right? Okay, that's not good. Where is that? Can you tell me which question number that where you had to do a lot of iterations? So all the answers here I'm seeing only like 3 or 4 iterations. I don't know why you had to do 10 iterations. Question 1, iterations. Question 2, there are 5 iterations. Question 3 is notation. Question 4, 3. Question 5 also 3. So all of the answers I have is less than 5. But I will double check and make sure that you don't have to do. I will make sure the questions don't bring you that kind of situation where you will just be stuck doing a lot of iterations. So the error here is like that. So let's say this error is, I'm going to put some number like this error is 5, this is -6, because if it is above it, it is okay. Okay, so yeah, you can, if you have, you can always contact me during the exam, but I'm not expecting you to do 10 iterations by hand. You can just put a note there, saying that I'm only going to do 2 or 3. It won't be more than 2 or 3 iterations. Okay, let me put some numbers to this error. Let's say it is -4. This is 1. I'm doing approximate numbers. -3, again 0.5, and -4. So, if I sum all these errors, sum of errors, will be 5 plus 1 plus 0.5 -6 -4 -3 -4. That is a sum of errors. And then we can have a square of errors. Square sum of errors. 5 squared plus 1 squared plus 0.5 squared plus 6 squared plus 4 squared plus 3 squared plus 4 squared. So, these are 2 different objectives. One is square sum of error with a sum of errors. If it is sum of errors, let's say you have one error that is 10, another error that is -10, and the sum of errors would have been 0. So we had a fitting. That was like this. It was like this, 10 and -10. But our fitting error will be 0. So that's not a good objective. So that's, there are different pros and cons, but this comes to this least sum of square errors. If you can reduce the sum of square errors, that'll be better than many other methods. So that is what I discussed here. So you can minimize the sum of all residual errors. And then you can minimize the sum of absolute value of errors. It is, you can minimize the sum of square errors. Compared to all of these, minimizing the sum of square error is better. So that is what we're going to do. And that is what's called the least square error. So what we will be studying, so based on this, we will be doing the least square errors fitting. So having introduced that, so let me go to the linear least square error problem. So sometimes this is, we also have an alternating, that is linear regression. So that least square fitting is, another alternating name is least square. So we will be using least square fitting to solve this linear regression problem. So for this, the error, sum of square error is defined as, sum of square error is defined as this. That is the sum of square error. I is equal to 1 to n because we have n data points. yi minus a0 minus a1 xi, whole thing square. So let me write that down here. maybe I write here. Okay, so that's the SR. Okay, I will just highlight it so you can see. This is SR. SR is EI squared. EI is the error. Yi minus A0 minus A1 Xi, all things squared. Now, our goal is to find A0 and A1 such that SR is minimized. So we want to, so obviously for certain values of A0 and A1, SR is going to have higher values where some place SR is going to be, let's say this for A0, it is minimized. So what is the point? So we already studied optimization. So to find that, if you have two variables, you just take, considering that other variable is a constant, take a derivative with respect to the desired variable. So let's look at this function SR, and let's take a derivative. So if you take a derivative of 4 with respect to A0, so A0 is here, it is a summation and it has A0. So, but you can take that derivative considering the summation, then that will be 2 times yi minus A0 minus A1 xi, and then derivative of A0, which will be -1. That's why you have -2 in front. So we take a derivative and set it to 0. So we get one equation. Similarly, we can take derivative with respect to A1, and then we'll get another equation. So now we have two equations and two unknowns. Unknowns are A0 and A1. So let's if you rewrite the equation in that fashion, so I can just -2, I can just get rid of because it is 0 to the other side. So then if I just expand, that would be this term correspond to this term correspond to this term correspond to this. Similarly, we can write this term correspond to this term correspond to this, and this term correspond to that. So we will get, you can simplify it. So from that, we can write equations 9 and 10. So you should always keep in mind that the unknowns are A1 and A0. These are the unknowns. So that we want to solve that. We want to solve for A1 and A0. So that's our goal. Everything else is known. N is known. N is how many data points? Xi is known. That is the data we have. Ya is known. That's the way data we have. So we have the data, and we just need to solve it. So this is very similar to the linear equation. If we have two equation and two unknowns, we can solve them. We studied many methods to solve them. Gaussian elimination, value decomposition, all those methods. You can also use the software to solve them as well. Okay, so so from this, we are just writing this. If we just solve this, since it is two unknowns and two equations, we can solve it in closed form. If it is 3, it's going to become a bit harder. Basically, what we are trying to do is, if we have an equation x1, a1 x1 plus a2 x2 is equal to b1, a3 x1 plus a4 x2 is equal to b2. If you have to solve for x1 and x2, you can get a closed form solution. That is what we are doing. So you can solve it, but we did not show the answer, the steps here, because it is 2 by 2. But if you solve it, and it is going to be like that. So a1 is going to be n times I is equal to 1 to n xi yi minus I is equal to 1 to n xi is equal to 1 n yi divided by n times xi squared, and then summation of xi whole thing squared. In a compact form, we can write it as, if you divide this by n squared, if you divide this by n squared, 1 over n, then n squared, 1 over n whole thing squared. So that can be written as xy bar. So no, I am x. When you divide that, then it comes to this form. That is summation of xi yi, and summation of xi yi divided by n, and be written as xy bar. So you take x summation, take multiplication of xy, all of them, take the average xy bar, and then this is x bar, and then this is after dividing by n y bar, and this one after dividing by n is x squared bar, and then this one is x bar squared. So similarly, we can also substitute for a1, and you will get a formula for a0. You will see that this can be simplified to y bar minus a1 x bar. So that's how you solve for a1 and a2. Now, I just used simple, or you can use Cramer's method to solve it. We know many methods to solve this, but here we just show one. So it is also important that the above can be written, especially this equation. If you look at this equation, this will become important later. If you look at that equation, so sy, let me highlight them. Sy is summation of y. If you look at it, that is sy. Sxy is summation of xy. So I will also highlight here the definition of sy. And then sxy, which is defined as summation of xi yi, that is defined here. Then sx, that is here. Sx is defined here, and also if you look at it, that is sx. Then we also have an sx here. Then sxx is summation of xi squared. That is xi squared. So that is sxx. So we can write an equation n, then two corners sx, and then next diagonal is sxx times a0 a1 is equal to sy and sxy, where all of these are known. This is known, n is known, how many data points, sx we can compute from the data, sx known, sxx known, sy known, sxy known. We need to find a0 and a1. You can use Cramer's method to solve it, or many other methods. So, but if you use it, and then this is the solution for a0, this is the solution for a1. That's it. That is how we do linear fitting. So, let me go to the example. Then I will come back and talk about the standard error of estimate and correlation coefficient, because these are kind of important. If you are going to learn anything about linear fitting, is what is standard error and what is the correlation coefficient, because everything else somehow somehow we know how to fit a line, how to write the equation, we know how to solve linear systems, but then how to put that in perspective is what is interesting. So I will come to that, but so let's do an example for what we study. So example here. So fit the following data to a straight line. So example is asking us to fit some. So let me do plot these data so that we can see example. So we are given 1, 2, 3, 4, 5, 6, 7 data points. 1, 2, 3, 4, 5, 6, 7. So that's X, and that will be Y. So 1, 2, 3, 4, 6. So for 1, it is 0.5. So it's somewhere here. For 2, it is 2.5. So 1, 2, 3, 4, 5, 6. For 2, it is 2.5. So, oops. So for 2, it is 2.5. Should be somewhere here. For 3, it is 2. 4, it is again 4. 5 is 3.5. 6 is 6. 7 is 5.5. So that's the data. If I have to fit, roughly, I would fit a line through this data. That line will be something like this. That is how it looks. Obviously, I drew this approximately, but roughly, I can say, based on what at least I drew this pretty accurate. I mean, so if this line is, our goal is to find y is equal to C0 plus C1x. What is C0 and what is C1? But by just looking at the things that I draw here, I can say that C0 is very close, small number. Probably it won't be close to 1, but I can definitely say it is less than 1. C1, I will say approximately 1, because we had many points where, 3, 2, 2.5, 4, 4, 6, 6, that means the gradient is 1. So approximately. So that's my guess. These are my guess. So this is guess. Now let's see what we get. So for this, we already know. We already have a formula for the solutions. We have a formula for solution which is A0 is Sxx Sy minus Sxy Sx over n times Sx minus Sx squared. Or we have multiple formulas for A0 is y bar minus A1 x bar. Where A1 is this. So all you have to do is compute this. Sxx, that is Sxy, xy, and then sy and sx. Maybe use all of that, and you will get just substitution here. A0 comes to 0.07, and A1 comes to 0.83. So we guessed that. So okay. So this is A0 and A1. Just to keep the same notations, A0, A1. So I guessed A1 is going to be close to 1. The A0 is going to be less than 1. So what we got for A0 is this and this. I mean, this is not a guessing game, but I just want to explain what is fitting. So, I mean, based on approximately, we see we get the data. I mean, it shows that we are fitting a line to the data. That's all. Now, so what we did, we used this formula that I showed here to fit these lines. Now let's go back and then try to understand about these errors. Standard error. What is standard error? What is standard deviation of the data? And how that makes sense. So standard error, the standard error of the estimate is given as after we estimate A0 and A1. So after we estimate A0 and A1, we can compute this. So that is the least. I mean, in least square, we try to minimize this error. Yi minus A0 minus A1 x. So that's a fitting error. So whatever we get here, that is fitting error. So we call this the sum of the error squares. The sum of error squares is A0 and A1 that we got from the data. We estimated them from the data. So yi minus A0 minus A1 xi is the error, and we square it because this is least squares. That's the approach we are using. So that error, and then we divide that error by n minus 2. The y n minus 2, it comes from statistics, but you just, in this case, you just need to know n minus 2. When we go to third order polynomial, for example, this is the first order. When you go to second order, it will be n minus 3. When you go to third order, it will be n minus 4, like that. That you just need to know. Y is beyond the scope of our course. So, but this is the fitting, this is called the standard error of the estimate. So we call this the standard error of the estimate. So this is the square error. The square error will, if you have more data, the square will increase. Because if n is 1000, compare n is 10 to n is 1000, when we have more data, this error will increase. Now that doesn't give us a good sense of is it a good fitting or no. That's why we divide by the n minus 2. So if we have more data, we divide by the number of data. So this standard error will always be between something. So that is the standard error, SR divided by n minus square root of SR divided by n minus 2. N is the number of data points. So probably I should say that n, because sometimes I use small n. So n is the number of data points. So that is the standard error of the estimate or standard error of the fitting. Both are sometimes used. And then another error we have is the total sum of squares. So you get the data, and you just take the yi, get the yi's of the data, and then you just find the mean of the data, y bar, yi minus y bar. So that's basically the variance in the data, yi minus y bar square. So that is the total sum of squares, not really variance. Variance has a special meaning in statistics, but it is called the total sum of squares. So look at the difference. So first we have SR, which is the sum of error squares, that is the fitting error square, and ST, that is the total sum of square, where we did not do any fitting. Yi minus the mean. So there was no fitting at all. So ST corresponds to no fit. And also we can standardize it. We can standardize this by dividing by n minus 1. So it's also important, for the sum of squares, it is divided by n minus 2. For this one, it is divided by n minus 1 because we didn't use any model in there. So now, okay, let me also introduce the correlation coefficient. So that is ST minus SR over ST. That is the correlation coefficient. If the ST, the standard ST is sum of square versus the fitting error, standard fitting error. So this is the standard error versus standard fitting error. If they are the same, then correlation is 0. Then if they are the same, which tells us that the variance was the same even after fitting. So that means the fitting did not help at all. It helped 0. So that is when we will get R is equal to 0. So R is equal to 0 means the fitting did not help at all. Whereas if SR is equal to 0, then this will be R is equal to 1 if SR is equal to 0. So let's go back and see what SR is equal to 0 means. So SR defined here is equal to 0 means yi is always equal to A0 plus A1x. So yi is always equal to A0 plus A1x. Let me draw that scenario. So let me, if I just Let me draw two scenarios, and I'm going to ask you which one corresponds to it. I'm having one scenario where we have some data points, and then I fit a line. I fit a line through these data points. Then I have another scenario. All the data goes to the line. So what is the SR is equal to 0, SR is equal to 0, where it is true? Case A or B, where the statement is true? That's a good question for a quiz. Can someone tell me? SR is equal to true is the statement is true for A or B. We want to take a look at what is SR. SR is here. Yi minus A0 minus A1x. So Alex is answering B. Let's see if it's true. Yes. So if you look at any data, yi minus A0 minus A1xi is always 0 because yi is equal to A0 plus A1xi. That is perfect fit. All the data are on the same line. So that was perfect, but in real world it won't happen. But we'll be close. If the data is really a straight line, we'll be close. That'll be a small number. So let's go back now. Let's go back now. So if SR is just, we want SR to be a small number. SR is small. If SR is small, so let's think the extreme case here. If SR is very small, then let's say SR is very small, then this comes to ST over ST, so that comes to 1. So the correlation coefficient is equal to 1 means really good. So every time we do a fitting, so now we know how to check it. We will compute the correlation coefficient and see it will be a number between 0 and 1. If it is 0, very bad. It is not, we didn't make a mistake that the data is such, the data is very noisy. That's why the fitting didn't work. Maybe we will think, oh, instead of fitting a linear line, maybe we should fit a polynomial because the correlation is not very good. So that's a good way of checking the data, because sometimes the data comes, in real world, you will have some data, you don't know whether to fit a straight line or the second order polynomial or third order polynomial. So we have to decide. So maybe we can decide based on the correlation coefficient. So that's the idea behind the correlation coefficient. So, okay, so that's it for linear fitting. Now let's go. You will see that that's all here. The remaining is some extension of what I just talked about. So before I go to this linear regression of nonlinear function, let me go to polynomial fitting, second order polynomial fitting, because it is very similar. So instead of, let's say we had some data point that looks like this. So the data already tells that, okay, fitting a line, straight line is not a good idea. Maybe, you can fit a straight line, but if you, after fitting the straight line, if you compute SR, that'll be a small number telling us that the fitting is not good. But if you fit a quadratic function and compute SR, that will be very close to 1, telling that is a good fitting. But I haven't defined what is SR for a polynomial fitting. So let's introduce the second order polynomial fitting, and then we will do an example. But you should always keep in mind that at the end of the day, you're going to compute SR to see the goodness. So sometimes it is got the goodness of fit. So SR is, maybe we can just fit, if you're given a mystery data and ask you to fit with us something for future lab, and then you will just well, that's a good point, but I don't have a lab like that. Definitely a lab for next year. Yeah, that's a good point. Maybe I will I will think about if I can make a project out of this. But let's see. But yeah, that's a very good point. I mean, that's how you do fitting in real world. Just try different things and look at the performance metrics and then iterate. So yeah, that's a good point. So so let's first of all let's look at the math. So if it is a quadratic so polynomial regression second order, once again, so regression means fitting equation through one data points. So we're going to fit for a given data point. So data is the same, x and y, x1, y1, x2, y2, all the way to xn, yn, like the one shown in figure 4. And if you want to fit a polynomial, second order polynomial, first of all, a second order polynomial will be second order polynomial will be y is equal to a0 plus a1 x plus a1 x squared. X squared, that's why it is second order. So then the error will be this yi minus a0 minus a1 xi minus a2 xi squared, everything squared, and you get a sum. That is the square error. Again, this is least square fitting. Now to find a0, a1, and a2, you have to take derivative with respect to a0, a1, and a2. So if you do that, then you can set them. You set them to 0, set them to 0, set them to 0 to find a1, a2, and a3. So you will get three equations. First equation, second equation, third equation. You can rearrange this and then write it like that. So now compare this equation 50 to this equation, the same, maybe 17. There is a pattern there. First, I used capital N and small n interchangeably. I should change this in the lecture notes. I will do it next time. So n, sum of xi squared, sum of xi to the power 4. Okay, I will highlight that. So n, sum of xi squared, sum of xi to the 4 increases into. Then on the left to right, xi squared, and then xi squared, xi cube, xi squared, xi cube, xi to the 4. So if you look at it, there is a pattern here. And let me draw a line of pairs. So these two are the same, these two are the same, these two are the same, and then they go down. If I just go back to the second order one, it is very same. And so n sxx, which is xi squared, and sx. Now let's look at the right side. Right side, y, xi yi, xi squared yi. So there's definitely, let me go to the third order. It is the same, the same idea. If I go to the third order, look at this. N xi squared, xi to the power 4, xi to the power 6. And then left to right, xi squared, xi cubed. And then start with xi squared, xi cubed, fourth. Start with squared, third, fourth, fifth. Start with third, fourth, fifth. And you can see that there is a symmetry here. These two are the same, these two are the same, these two are the same, and then these two are the same. Then these two are the same, and then same here. So it diagonally increases squared, fourth, and sixth, and then correspondingly it goes up by 1. So obviously, for third order polynomial, in the general form will be yi is a0 plus a1 x plus a2 x squared plus a3 x cubed. So we want to find A0, A1, A2, and A3. So that is can be put in here. So this is for third order equation 59. Equation 50 is for second order. And then equation, any of these, maybe 28. And maybe because at the start I had explaining so much, 17, all of them the same. That is first order. So there is a pattern, we can write it. And we borrow a lot from the we can write this in x time a is equal to b, where we had to solve for a. You can use Cramer's method, for instance, to solve it. If you are given a bigger question like this, this is a 4x4 system. Definitely, either you can use Cramer's method, and you need a computer to do that. For a 4x4, you need to find a determinant of 4x4. I will never ask that to do it by hand. But definitely I can probably ask it as a homework question. So I first introduced how to compute the values. Let's go back and let's see how to compute the standard error, because that's the important thing. I already introduced standard error as an important metric. So we studied about 4 things: ST, SR, SY given X. ST and SR are the important ones, and then R. R is the correlation. At the end of the day, we want to compute R correlation coefficient. So the definition of correlation coefficient is the same. ST minus SR or ST, always the same. SR is not going to change, at least intuitively. Earlier, in the first order, it was Y0 minus A0, A1x, all things squared. Now Y0 minus A1, A0, A1x, A2x squared, obviously because this is a second order fitting. And then what about ST? ST is also not going to change. I did not have ST here, but the definition of ST is the same, which is yi minus y, right? So probably I should, the definition of ST is not going to be changed. It is the same, yi minus y by all things squared, summation of. Okay, so then the equation of ST and SR, you can it's very similar, and then based on that you can compute the correlation coefficient. Now SY given X, and then S the standard error of fitting, it is another way of filling out. I mean that number alone will give us a good feeling about the fitting. That probably comes with some experience, but probably this figure will tell us, the error. If you think about a distribution, this is the standard deviation. What is the deviation? How much away from we are from the data? So if you have a good idea about the data and expected standard deviation, this Sx, Sy, and then Sy given X will give, you can compare them. The comparison between Sy and Sy given X is very similar to the comparison between Sr and St. St is Sy is very much related to St, because look at the equation. Sy is an indicator of St. Sy given X is an indicator of Sr. If Sy given X, the standard error of the estimate, if it is less, if it is a small number, then the fitting is good. If Sy is a small number, it doesn't really mean anything except the data doesn't have a lot of variance. Sy can be a large value, it doesn't matter, but if Sy given X is small, that is good. But at the end of the day, we should only look at the correlation coefficient, because that tells a lot about the fitting. Okay, so I covered, these are very similar things. Once you, probably when you study, you can just take a look at the linear fitting and then see how, when you increase a model order, the pattern repeats. I mean, there's a lot to do when you understand this. For example, you had to understand how this error is defined and how what is our goal. Our goal is to optimization. This is another lecture. Optimization means we take a derivative and set it to 0, assuming that it minimizes. But these are all theoretically proved. So then it comes to this linear system of equation, and then we solve them. So we know how to estimate these parameters. And then to check how good our fitting is, we compute the fitness of goodness of fit. That is SR. And then the SR is close to 1, our fitting is good. If SR is close to 0, fitting is not good either. We had to increase the order. Well, it is always mean if the fitting is not good, we have to increase the order. Okay, so that's it. And I need to talk about one more thing. That is, there's a small discussion about what to do. Sorry, I'm just moving up and down. Okay, that's the last place. I won't move too much. Okay, so there's a topic here about linear regression of nonlinear functions. So if we have a nonlinear function, so I mean, let me spend some time there. What is a nonlinear function? You might confuse because we are fitting if it is second order polynomial. If it is second order polynomial, we are fitting y is equal to a0 plus a1 x plus a2 x squared. So we are fitting this. That is second order. That's not linear. Then why are we calling it linear fitting? Can someone tell me? So why this is a linear? We are fitting a polynomial line, but the function is still considered linear. Why? That is because I can write this as 1 x squared a0 a1 a2 as a vector. We studied metric, so we know this is y is equal to some a times x form. If we are in this form, we call this, for example, this is, we have to estimate for x. Need to estimate for x. So if we have a system where y is equal to, we have a system where y is equal to ax, where we need to estimate x, that is for linear system, then we can use, that is how it came, the final equation came. The reason is that even though we have x and x squared and x cubed and all of them, but these are given data. What is unknown always comes in the form of a summation. That's why this linear equation. But there are cases where the linear equation won't work, and we need to do nonlinear equation. One example is here, exponential equation. So here, we had to fit the data x and y, for y is equal to alpha 1 e to the power eta 1 x. So if you are given pairs of x and y, x1, y1, x2, y2, x and y. So the question is, fit this data to this function, and what we have to estimate, fit the data above data and estimate what parameters we have to estimate. If I fit y is equal to a0 plus a1x, I would be estimating a0 and a1. If I fit y is equal to alpha 1 e to the power eta 1 x, I will be estimate alpha 1 and eta 1. That estimation is not possible through the linear least square approach that we studied so far for like polynomial fitting, second order polynomial, all of that we can estimate using least square using the same equation I taught. But we can convert that into a linear estimation problem. Why? How? As it is shown here. Take log on both sides. When I say log, most of the time I mean ln. But I changed that in the lecture note to make sure that's that remains the case. So yeah, so it's ln y. So ln y is equal to ln alpha 1 plus eta 1 x. So if you look at this, now if I make this as y and this as x, so if you look at this now, it is in the form of y is equal to something times x plus ln alpha 1. So that is in our regular notation. This will be a0, that will be a1, and these are the data. So instead of fitting x versus y, we will fit x versus ln y. And if you have a power equation, so this is called a power equation again. It's very similar. Y x to the eta 2 alpha 1 e to the eta 1 x. So there's a small difference here. If you look at this, that is if you take ln on both sides, that comes to ln y is equal to ln alpha 2. Ln y is equal to ln alpha 2 plus eta to ln x. So instead of fitting y versus x, we will be fitting this is our y, this is our x. So what we will be estimating? We will be estimating this will be a0, and that will be a1. And then here is another example. Y is equal to alpha 3 times x plus eta 3 plus x. So for that, if you just divide by 1 over, if you just reverse it, this becomes 1 over y is equal to 1 over alpha 3 plus eta 3 over gamma alpha 3 1 over x. So now this is our new y, this is our new x, and then a0, a1. After you estimate the a0, for example, we know that a0 is equal to eta 3 over alpha 3, a1 is equal to 1 over alpha 3. And so we won't be able to estimate. Oh, okay, we can estimate both because there are only two unknowns. So from a0 and a1, we can estimate alpha 3 and eta 3. So those are some examples for nonlinear fitting. So that's it for the lectures. And I have some questions. I have 4 questions, but I did not assign all of them as homework. Probably assigned 1 and 2. Some of these homeworks, these questions were used as a for final exam in the past. So that should give you an idea, and not sure what to do. So practice this, and always, make sure you understand the lecture notes. All right, that's it for this lecture. If you have any questions, I have some time. Questions about anything? Expectation. What do you mean? Can you explain a bit further? What kind of expectation are we talking about? Yes, finding the lines. The question will be very similar to homework. For a given problem, finding the lines of fit, and then giving an opinion about the goodness of it. How good the fit is. For example, I'll give some data. I'll ask you to find a linear polynomial, and then I'll ask about yes. So how can you just give some opinion about your fitting, and then you can just compute the correlation, and based on that, if you can For a given data, if you can fit any line and then compute the correlation, and then that's all that we needed for the course. All right, everyone, if there's no questions, so as usual, so the homework for this question is already available. You can start doing it, and the next lecture will be recorded for Thursday. Next lecture is on interpolation method. So the difference between interpolation versus regression is that, given some data points, here we just fit a model for a given data. We fit a model. So I just first example, so just given some data point, you fit a model, whether it is straight line or it's a curve or it's a polynomial. That is this lecture. Next lecture is if you're given some points. You're given some points like this and this, and so that is x1, that is x, and x3, and for new point x4, what is the y? X1, y1, y2, y3. For new x4, what is y4? That is called interpolation. There are many methods of interpolation. We will see that the interpolation approaches that we will study, that would be much more better than these lines. And then most of the time, interpolation needs to be done based on 2 or 3 lines. So that way, there are very specific approaches that will do much better than these line fit approaches. So line fit approach will be less effective. That's why we have a separate discussion about interpolation. So we will study many different interpolation approach, and then that will make when you see them, you will realize, and they are very structured as well. All right, everyone, and I look forward to the meeting on Tuesday, and please expect lecture videos on Thursday.